We'll just wait one more minute for any stragglers. So I'm going to be assuming a working knowledge of 11-dimensional string theory, advanced calculus, linear algebra, and there will be a quiz. Let's try. So, morning everybody. My name's Rob. I'm a lecturer in physics based jointly between Sussex University and Royal Holloway University of London. Strictly speaking, I'm a particle physicist, not a astrophysicist or a specialist in black holes, but I have worked a lot on black holes as part of my research. So, while we're going through things, by the way, I would love questions. So I have left some time at the end for us to have questions, but if anything comes up and you just can't bear to keep it in for any longer, please do put your hand up or shout out and we'll have a chat about it. Okay? So, what are we talking about today? Black holes. So black holes are some of the most dynamical and interesting and violent objects we know of in the cosmos. Their history is fascinating. For a long time it was thought that they were mathematical artifacts coming out of Einstein's equations, and it's only really in the last 50 or 60 years that people have begun to appreciate that these are real astrophysical objects, things that we can see and we can detect, and perhaps even one day to visit. So we're going to start off by talking a little bit about Einstein, and about Einstein's major breakthrough in the early part of the 20th century that lays the foundation for black holes. So Einstein, he has lots of great ideas. The greatest of his ideas is not even what he wins the Nobel Prize for. So Einstein wins the Nobel Prize for a sort of quite subtle explanation of how when you shine certain kinds of light on a certain kind of metal, it makes sparks. So what he wins his Nobel Prize for is actually seemingly more minor than his real breakthrough, which is his theory of gravity, Einstein's theory of general relativity. So prior to Einstein, our knowledge of gravity comes from Newton in the 17th century, who describes the gravitational force between two objects. Gravity is a force that affects objects with mass. Please come. And it only affects objects with mass, and it's only attractive. These are the two sort of key ideas of Newton's theory of gravity. But a few hundred years later, Einstein develops his incredible framework of general relativity, which he publishes first in 1915, which describes gravity not as a force, but as a curvature of space-time. Rather than thinking of the force of the sun pulling the force of the earth and maintaining an orbit, we think of the sun as indenting the fabric of space, and the earth as sort of rolling around the rim of this indented fabric. And this gives all sorts of other predictions that Newton's theory cannot capture. For example, Einstein's theory predicts that gravity should be able to bend light. He also predicts a very subtle deviation in Mercury's orbit, which for hundreds of years had remained unexplained. So an observation was made about Mercury's orbit that when it orbits around the sun, the point at which it is furthest from the sun shifts by a small angle every year. So it sort of makes one of those spirograph patterns, if you've ever done one of those spirographs, you know, you stick a pencil in and it's on a gear and it makes a little pattern. And Einstein explains this for the first time. So his theory is radical. First of all, it relies on considering time to be the fourth dimension. So he's putting time on an even footing with space in a way that has not previously been done. But it makes predictions that are measurable. And this is the key thing in science. If your theory is crazy, or rather go the other way, no matter how beautiful your theory is, no matter how wonderful your theory is, if it disagrees with experiment, then it's a bad theory. Likewise, if it agrees with experiment, if it makes predictions we can test and we can confirm, it's a good theory. So general relativity is a good theory. Now, the language that Einstein writes general relativity in is this extremely complicated language called tensor calculus. And this is a branch of maths that is barely even studied if you do a degree in physics. So it's extremely advanced. And the equations he has are very difficult to solve as a result. But about a year after he publishes his equations that describe the curving of space in response to matter, another German physicist called Karl Schwarzschild finds a solution to these equations. He solves Einstein's equation, and he looks at his equations and he says, what is this telling me? And the solution to this equation is where black holes come from. This prediction of Einstein's equations, found by Karl Schwarzschild, predicts that when matter collapses beyond all possible prevention and continues to collapse and continues to collapse, we form these extremely exotic objects we call black holes. And another consequence of Schwarzschild's solution is he finds an expression for the size of the black hole, the radius of the black hole. So this involves a few constants. It involves, first of all, the mass of the black hole, so bigger, heavier black holes are larger, generally. It involves this constant g, which is actually called Newton's constant. So this is a constant that's been known about for a few hundred years from Newton. And it involves c, the speed of light. So light is fundamental to Einstein's theories. This is how he first starts thinking about space and time, thinking about what it would be like to run alongside a particle of light. What would you see? What time would you experience? So light is fundamental to Einstein's theories. Now, Schwarzschild's solution, as I say, it describes this ultimate outcome of the collapse of matter. But initially, people don't believe in this solution. They think, sometimes you solve an equation and you get an answer, but it doesn't necessarily mean anything physical in the real world. And the consequence of this collapse we call a singularity, this point of infinite density, the end point of all collapse of matter. Einstein himself didn't believe in these. So Einstein himself was very skeptical about this ultimate consequence of his own equations. However, we did, of course, later confirm that these are real objects. Black holes are real physical objects we can see in the universe. So let's discuss a little bit more about what a black hole is. So the anatomy of a black hole is actually not very complicated. Describing them, the maths behind them is complicated, and what they do is complicated. But actually, from the outside, they are remarkably simple looking. There are two main components to a black hole: the singularity, which we'll talk about shortly, and the event horizon. So the event horizon is the boundary between what lies within the black hole and the rest of regular space and the rest of the universe outside. So, as I mentioned, Schwarzschild derives this formula to calculate the size of the black hole, for the radius of the black hole. This is the distance between the center and the outer edge of the event horizon. But again, as of yet, it's not yet known whether these objects are actually real. So, first of all, the horizon. The really interesting thing about black holes is that this horizon is one way. Okay? Things can fall into the black hole, they can pass beyond the horizon to the interior, but nothing can pass out of the black hole. It's completely one way. Nothing can come outside of the black hole. It violates the laws of physics. There's a very small exception, which we might talk about at the end, which comes to us from Stephen Hawking, but generally speaking, nothing can escape the black hole once it passes within. Another feature many black holes have is this wonderful accretion disk. So, because things fall into a black hole and nothing can fall out, a lot of matter tends to spiral inwards. Falling in, as it falls in, it keeps its angular momentum, so if it's spinning before it falls in, it's spinning as it falls in as well. And these layers of gas and dust, as they spiral in, they rub up against each other, and they, by friction, they generate an enormous amount of heat. And this produces a sort of glowing, spiraling disk of material in falling into the black hole. So this is a real image of a real black hole. This is actually the black hole that lives at the center of our galaxy, the supermassive black hole called Sagittarius X star. And you can clearly see what we're looking at here is actually the accretion disk. It's this disk of hot, in-spiraling matter. that falls into the black hole. The reason black holes are so difficult to detect if they don't have this accretion disk is that obviously space is black and black holes are also black. So how could you possibly, there's no contrast, right? You can't tell the difference. The singularity. Now the singularity, this is the key. This is the part of the black hole that I really can't tell you very much about because we don't know very much about it. This is a point of infinite density. This is the end result of all of that matter, all of that gas and dust collapsing inwards towards a single point. This is where the laws of physics break down as we know them. Unlocking the mystery at the center of the black hole is one of the main goals of modern physics. But it's a difficult goal because it straddles two very important theories of 20th century physics. So 20th century physics is built on two pillars. Quantum mechanics, which describes things that are very small. It's what allowed us to understand the atom and nuclear physics and develop the atomic bomb and atomic energy. And the second pillar is Einstein's theory of general relativity, which we've just been discussing. And this works very well for very large things, for things like the orbits of the planets, and it works for stars and galaxies and things like that. But the difficulty with a black hole is that a black hole is both very tiny and very heavy. So one of the theories is not good enough in isolation. You need a combination of the two. You need a theory of quantum gravity, something that can describe things that are very tiny, like this infinitely tiny singularity of a black hole, and things that are very heavy, because as we'll discuss in a moment, where do black holes come from? They come from collapsing stars. So a singularity of a black hole is something with the weight of a star compressed to a tiny point, smaller than an atom. So it very much straddles this very difficult area between the tiny and the heavy, which only quantum gravity, whatever that might look like, can describe. And we don't know what this theory is. I don't know what the equations of quantum gravity are. If I did, I wouldn't be here. I'd be on my way to meet the King of Sweden to collect my Nobel Prize. But this is the goal. This is the theory of everything that is sometimes spoken about in physics. So, where do black holes come from? Well, they come from the stars. So, stars, much like people, have a life cycle. They have a sort of standard middle age where they're in a very balanced state, where the forces of nuclear fusion that are trying to explode the star outwards balance the forces of gravity trying to squash the star inwards. They have a slightly more turbulent old age as a red supergiant where they've expended all of their hydrogen fuel. They're now having to fuse helium within their core, and their layers have expanded extremely far. So, for example, our own sun will never be a red supergiant, but it will be a red giant. And when it gets into this phase, its radius will extend roughly to the orbit of the Earth. So if you think about how big the sun looks in the sky now, imagine the edge of the sun expanding out, into your back garden. That's how large the sun will become when it expands. And very, very large stars, once they've expended all of the nuclear fuel within their core, will undergo a supernova. So this is the death of a star. The inner layer, the inner core explodes and it catapults the outer layers into space, leaving us with some of these wonderful nebulae, these clouds of glowing gas and dust. I believe this is the Crab Nebula here. These are the graveyards of dead stars, these structures. And if the star is large enough, not only will it leave behind this cloud of gas and dust in the form of a nebula, but it might leave behind a dead core, this black hole, where the collapsing core of the star cannot be prevented. It's so heavy and so dense that it collapses and perpetually collapses. It continues to collapse interminably and forms this black hole, this point of infinite density, the mysterious singularity, shrouded in this cloak of the event horizon, this one-way street that only can be entered but can never be exited. Now, as we said, Schwarzschild and Einstein, they have their equations. They predict something like a black hole from the equations, but it's not quite believed that these things could actually form in the real world, because when they do their equations, there's a joke about physicists and spherical chickens. If you ask a physicist to help solve your problem on your farm, he'll give you a solution that works in a vacuum if your chickens are perfect spheres. And this is sort of similar for Einstein and Schwarzschild. When they work out what happens when a star collapses, they have to assume the star is perfectly spherical and it's made of one composite element and so on. They make lots of quite unrealistic things. But obviously stars are much more complicated. The sun is made up of lots of different elements, it's turbulent, it's hot, it's difficult to model. But these very smart chaps, who I've met both of them, come along, Roger Penrose and Stephen Hawking, and they managed to show that actually, even in an imperfect world, where stars are not perfectly spherical, there is a way that a cloud of gas, like a star, can collapse and continue to collapse into a singularity and form a black hole. So these come from Hawking and Penrose's singularity theorems, where they prove that singularities are admissible in the real world. Okay, so now black holes are on a slightly more realistic footing, where they could conceivably exist in our universe. And just as a side note, an example of where you find these black holes, every single large galaxy in our universe, we believe has a supermassive black hole at its center. It's thought that these are crucial in how galaxies form, in ways we don't yet fully understand, but we've not yet found a galaxy that we don't think has a supermassive black hole at its center. We know it's there even if we can't necessarily see them by the gravitational influence that it has on the surrounding stars in the center, because black holes are enormous sources of gravity because they have this extremely heavy mass coming from a collapsed star. Even if we can't see them, we know they are there based on their gravitational influence. Now, sometimes these black holes are extremely active. So this is an artist's illustration of what's called a quasar, which is a supermassive black hole at the center of a galaxy, which has a very, very strong, very, very large accretion disk, as we mentioned. And due to this sort of spiraling in of this accretion disk, it generates very large poles of X-rays as well. So you have X-rays shooting out of each pole of the black hole, which we can detect. This is one of the first ways we actually detected black holes, was by seeing these X-ray pulses, just X-ray beams coming towards us from centers of galaxies, from these quasars. Okay? And by the way, supermassive is a technical term, which means roughly between 100,000 and a billion times the mass of the sun. So these are not small black holes. These are extremely, extremely massive black holes. So, as an example, consider our nearest neighboring black hole that we know of. So this is a system discovered by the Gaia satellite. So about 1,560 light years away. By the way, light year is not a length of time, remember? Light year is a length of distance. 1 light year is how long light travels in 1 year of time. So, I mean, just to put it in perspective, it takes light about 8 minutes to come from the sun to the Earth. So 8 light minutes is the distance from the Earth to the sun. 1 light year is how far it travels in an entire year. So that's many thousands of times the distance between the Earth and the sun. Very far away. If you traveled at the speed of light, it would still take you 1.5 centuries to get there. Sorry, 1.5 millennia to get there. But if we think about this black hole that we know of, thanks to the Gaia satellite, we know it has a mass of about 9.62 times the mass of the sun. And don't worry if you're not following this maths. I just like to show my sums, but you don't have to follow this. This was the calculation I did earlier. So the mass of this black hole is about 9.62 times the mass of our sun. Mass of our sun is roughly 1.99 with 30 zeros after it in kilograms. So I'm using here Schwarzschild's formula for the radius of a black hole. I do the calculation, and I find that the radius of this black hole is about 28 kilometers. So to put that into perspective, if we were sat at the singularity of this black hole, the edge of Gaia BH1 would be roughly at about the Dartford crossing. So next time you have to drive over the Dartford Bridge, you can think you're driving the radius of Gaia BH1, the black hole. So this is the size of the nearest black hole to us. But think about how small this is compared to how heavy it is. Remember, this is something that is nearly 10 times the mass of our sun, compressed into something that would mostly fit inside of Essex. So black holes are extremely dense, very massive, but very tiny compared to their size. Okay. Another example, consider the Earth. Now, black holes form when matter collapses beyond the point of any reversal, when they collapse to become so dense that gravity is so strong, nothing could escape, including light. How much would we have to compress the Earth in order to turn it into a black hole? So let's have a think. We're squashing the Earth down, smaller and smaller and smaller. At some point it will become so small and so dense that it will form a black hole. But what is that point? Well, I'm doing some more sums again. So I'm thinking about excuse me, the mass of the Earth. I'm thinking about Schwarzschild's formula, and my conclusion is a diameter of roughly 18 millimeters, which is about the size of a 5p coin. So, again, another impression of how dense a black hole is. This is something with the mass of the entire Earth, but it would be the size of a 5p coin. Okay? You could hold this black hole in your hand. And actually, there's no size restriction on black holes. Black holes can be very tiny. Some theories are trying to explain the nature of dark matter, so this mysterious material that is responsible for the way the galaxy spins and holds the galaxy together. Some people think that this might be billions and billions and billions of microscopic black holes left over from the very early universe, these so-called primordial black holes. We've not seen any evidence of that so far, but it's one of the many theories explaining what dark matter might be. So, black holes, very tiny, very massive, very tiny. Possibly the most interesting feature about black holes is how they affect the passage of time. So, this is one of the real revolutions of Einstein's theories of relativity, that time is not a fixed and uniform passage for everybody. Time runs differently depending on how fast you might be moving, where you might be stood. If you're very near to something very heavy, a black hole or a star, time passes at a different rate for you than it does for someone who's not where you're stood. So, for example, if we have these two people, person one and person two, who are stood at very different distances away from the black hole. So, person one is stood near to the black hole. I'm labeling them a distance r from the center, from the singularity. Person two, I'm going to say, is very far away from the black hole. So, effectively an infinite distance. So, if imagine this was the black hole that was 1,560 light years from us, so Gaia BH1, we were just discussing. We could be sat at home back on Earth as person two, and person one would be sat far closer to this black hole in orbit around it. And there's a formula. The formula, again, comes to us from Carl Schwarzschild and his solution to Einstein's equations, which tells us how the tick of a clock near to the black hole depends on the tick of a clock very far from a black hole. So there's a factor that multiplies the time far from the black hole to give us the time near to the black hole. They're not the same, okay? So 1 second for the person very far away is not the same as 1 second for the person very close. If you've seen the film Interstellar, I'm sure you'll be familiar with this, right? When he goes to the water planet that is very near to the black hole, he spends some time there and he goes back to Earth, and his daughter is now older than he is. So time has changed. The progression of time is not linear. It's not identical. So let's put this into perspective a bit and think back to Gaia BH1 and see if we can do some calculations. So back to Gaia BH1. Remember, this is the black hole that had a radius that extends roughly to the Dartford crossing. Let's now suppose we get in an orbit around this black hole that would take us to about central London. Okay? So again, this is not an enormous, crazy scale. These are scales we can kind of imagine. So we're orbiting around Gaia, this Gaia BH1 black hole, at a distance that would take us to central London. So let's do some calculations. So let's suppose we spent 1 year orbiting Gaia BH1. So this is us orbiting 56 kilometers from the center of Gaia BH1, and we spend a year there in our spaceship or whatever it might be. And the question is, for everybody back on Earth, 1,500 light years away, how much time has passed? So using Schwarzschild's formula, I do another little bit of maths here, and I find 1 year and 5 months. So this means if we spent 1 year orbiting this black hole, 1,500 light years away from the Earth, then everybody on Earth would have aged 5 months more than we had. So we would have traveled 5 months through time. And this is only a very small black hole, and a relatively far orbit from the center of the black hole. If you have a larger black hole, or if you orbit even closer to the event horizon, you can make this effect 10 times, 100 times greater. You know, you could travel hundreds of years in the future while only having to spend a few months around one of these very, very large black holes. So this effect can be multiplied enormously. How do we know this is true? How do we know this is true? It's a very reasonable question. My answer as a theoretical physicist would be because we did the maths. Here is some maths. But you might reasonably say, well, how do you know the maths works? We've never been to a black hole. We can't make a black hole in a lab. I can't, stick a probe or a thermometer inside of one and see what's going on. How do I know? Well, did any of you get here using Google Maps today? Anybody use Google Maps? Use a bit of Google Maps, Okay, so if you got here using Google Maps, you have proved Einstein's theory of general relativity just by getting here. So, GPS satellites around the Earth, these work by pinging a signal between your device, seeing how long the signal takes to return, and doing this with multiple satellites. They can triangulate your location and find out exactly where you are on the Earth's surface. Now, to do that, they need super accurate clocks in order to figure out where you are. But gravity changes the passage of time. This is what Schwarzschild's formula tells us. This is not only the case for black holes, where if you spend some time nearer to a black hole, your clock runs slower than someone else's clock. So someone far away, they get more ticks out of their clock than you do, because they've had a year and 5 months, you only had 1 year. This is not just true for black holes, this is also true for the Earth. For any object that has mass, time will behave in this way. So for your clock on the Earth in your mobile device, time is ticking at a different rate to the clocks on this GPS satellite that are trying to ping your location. Now, it's only a very small effect, but if you don't account for this effect, over the course of a day, a couple of days, suddenly your GPS satellite is hundreds of meters off. It's thinking you're in Dartford when you should be in Southend. It's completely got the wrong location. So we have to make corrections to the time on the satellite. We have to set the clock back a little bit to correct for the effect of general relativity, this time-bending effect due to the mass of the Earth. And if we didn't do that, GPS wouldn't work. So by the fact that we can predict how much the clocks on the satellites shift compared to the clocks on the Earth, we prove Einstein's theory of relativity every time we use GPS. So this is my I guess, slightly smart-ass answer to that question. But it's because predictions are made not just about black holes, but about other things. And we test these predictions, excuse me, and they turn out to be correct. We can make a prediction about what will happen, and then when it actually happens, it gives us faith, it convinces us in the accuracy of our equations. So when my equations also say, now if I do the same thing and go to a black hole, this is what will happen, I have good reason to believe these equations are accurate then as well. Okay. So, death by black hole. Let's think about this. So, consider two people stood by a black hole, one with his orange face and a stupid red hat, and person A is going to push person B into the black hole. So, there we go. Let's think about how this looks from each person's point of view. So, person A's point of view. This is the person who did the pushing, who is watching person B fall in. Now, from person A's point of view, person B never actually passes through the horizon of the black hole. Because of the way that time is slowed and changes for each of these people, what person A will see as person B approaches the black hole is a sort of squashing. This isn't person B hitting the black hole. There's nothing to hit. There's no solid surface here. But what will happen is he will approach more and more slowly, as the time ticked by this person's clock, the time ticked by this person's clock ticks much more slowly. Okay? So they approach asymptotically, very, very slowly. And if suppose they had some sort of radio communicating, so if person B was, talking and, sorry, might be later. Okay, so if person B was communicating and describing what he was seeing as he fell into the black hole, he would be saying, I'm not going to do an impression, he would be saying, I'm falling in, I can see the event horizon appearing, and I'm passing through, and it would go on and on and on. And the signal eventually would get so drawn out and so stretched that it would go beyond even the capability of the receiver. It would become stretched so far that it would go beyond radio waves, and the energy would all be lost, so he would stop communicating. Okay? Because the immense gravity near the horizon is stretching the wavelength of the signal. It's slowing down the time for this person as they approach, so that no communications would eventually reach person A. Person A could sit there for billions of years and they would never see person B fully past the horizon of the black hole. Okay? Because of the way that time is bent for these two people. What about person B? What would person B see? So, from person B's point of view, they can pass through the horizon actually without very much difficulty. Again, this is not a solid surface. From person B's point of view, if, I mentioned this term here, which is a technical term, spaghettification, which is serious. This appears in physics textbooks. But if the black hole is very tiny, then actually tiny black holes are much more dangerous than large black holes. As you fall into the black hole, the part of your body that is nearer experiences a much larger gravitational pull than the part of your body that is further away. So what the consequence of this is that as this person falls in, their head is being pulled far harder than their feet are being pulled. And if you imagine doing this to someone, this is why they get sort of drawn out and turned into spaghetti, hence the spaghettification term. So that happens to very small black holes. But if you have a very large black hole, then the gravity is a little bit more gentle, and you can pass through without coming to any serious harm. So if this person was able to pass through without coming to serious harm, what would they see? Well, as they sort of look back towards person A, the person that pushed them in, as they approach the horizon of the black hole, they would see this person move super fast. They would be moving very quickly and aging very quickly as well, hence the beard and the walking stick here. But not only that, it gets worse. As they're looking out, as they turn over their shoulder and look out towards the universe as their back passes through the horizon, they see stars go supernova. They see galaxies collide. They see the universe go from a very light place in this epoch we're in at the moment to a place of no light, dominated by black holes and dark matter, where stars are not close enough to collapse and form new stars. The universe becomes very rapidly, over the course of hundreds of billions of years, a very cold and very dark and very remote place. But the good thing is, once he's inside, he can't cry about it for very long, because then he moves towards the singularity. So after witnessing the heat death of the universe, witnessing billions of years pass in a matter of seconds, he heads towards the singularity. And there, I can't say what happens. If you extrapolate what we know about gravity and what we know about black holes to the singularity, we would say, well, he'll be shredded apart. You know, he'll collide with this point where it's been said God divided by zero at the center of a black hole. This point that makes no sense physically. The gravity will be so strong, it will rip it apart. But we can't say what happens. Maybe, you know, like Matthew McConaughey, he'll enter a fifth dimension and he'll go and visit his daughter's bedroom, and what, you know, that's what happens in Interstellar. We just can't say. But the interesting part is what happens when he passes through the event horizon. This is when he sees the entire future of the universe pass by extremely rapidly. Okay, so I think at this point we finished a little bit early. I think the aim was to finish roughly at 1:45, so we're only 10 or so minutes early. But does anybody have any questions? Is there anything we'd like to discuss or talk about? Yeah. So we've got a little bit more time for questions, but just in the very last couple of minutes, I just want to point out that there is another lecture I'm giving in April, which is on pulsars. The details of this are here. It'll be at 1 p.m. April 16th in this room. And then additionally in May, all of this will be on the museum brochures and on the social media. I'm giving a series of lectures throughout May, titled The Science of Space, Physicist's Guide to the Galaxy. So we'll look at lots of different things beyond black holes as well. And if you want to take a look at the lecture slides for this talk, they are on my website. So the website is just there, cosmicconundra.com. If you go on to Notes and Recordings, you can get these lecture slides if there's anything you want to check from there. Make sure I've not made any errors in my calculations. Okay? Well, I think we better clear off the room now, but I'll be outside if anyone has any other questions for a couple of minutes, okay?